Thank you. Okay, today we are welcoming Christian Ufrecht to talk about cutting multi-control gates using the ZX calculus. Please take it away.
Thank you. I guess I first have to go to full screen. Okay, thank you. Thank you for inviting me, and it's a pleasure to talk with you about ZX calculus and how we used it to do cutting of multi-control gates. So I heard that this is a quite informal seminar, but I prepared a lot of slides, and I guess I would just start going through the slides, and then you can just interrupt me and we can discuss if there's something to discuss. Before we do that, allow me to show you two slides on my research organization where I'm working at, which is Fraunhofer Institute for Integrated Circuits in Germany. So Fraunhofer is one of the largest research organizations in Europe for applied research. And I'm working in one of the institutes, the Institute for Integrated Circuits, short IIS, which is located in Nuremberg. And so the main research areas of this institute are microelectronics and information technology systems. But Fraunhofer is maybe most famous for the invention of the MP3 audio format in the 90s. Since 2020, there has been established a competence network for quantum computing, where Fraunhofer EES is also part. And there are just several institutes in Germany who started to build up quantum computing groups. And we have this partnership together with IBM, which allows us to have access to the IBM system close to Stuttgart. And I can also show you later results from experiments we did on this hardware. And so in the end, our group, at the moment, we have 5 full-time employees working on quantum computing, and the background is a mixture of computer science as well as theoretical physics. And our main topics are quantum machine learning, as well as the opposite, basically using classical machine learning methods to optimize quantum computers. For example, trying to use reinforcement learning to do compilation tasks. And we're also thinking about how one could combine that with tensor network methods or ZX calculus. So maybe if we have time in the end, we can also, or I can also ask a few questions about that if we have time. And with that, here's just an overview about about the slides I prepared. I have a few slides to introduce you into the topic of circuit cutting, if you're not familiar with that. We then do multi-control set gate cutting implemented using ancilla qubits. And in the second part, we can talk about ancilla-free implementations of these ideas. So I guess we start with a brief introduction into circuit cutting. So circuit cutting is about the decomposition of quantum circuits in such a way that they disintegrate into smaller partitions, and in such a way that the smaller partitions can be run on a quantum device. Consider, for example, this circuit here on 2 qubits, and this 2-qubit unitary, and we want to measure the observable O. Then, of course, the expectation value can be written as the trace over the observable times the time-evolved density matrix. And what we could do now is just replace these unitary matrices by a sum over factorizing single-qubit unitary, or a tensor product of single-qubit unitaries. For example, you can write a CZ gate as the sum over the tensor product of 2 S gates, 2 phase gates, and 2 phase stagger gates. Then we plug that in. But what you can see now is that there are terms in this sum where, for example, from the left there acts an S gate, and from the right there acts also an S gate on the density matrix. So not all of these terms correspond to actual valid quantum circuits. So we cannot run all elements of this sum on a quantum computer. So this is not what we want to do, but instead we want to look at the unitary channel corresponding to the unitary U, and we want to decompose it. So we write it as a sum over channels that factorize over the two partitions. So in this case, over these two qubits. And this means that in this case, all terms in this sum, we can write like, when we substitute it, all terms or all operations acting from the left and from the right on this density matrix are the same, or are the Hermitian conjugate. So this means that all these sums or all these terms in the sum can be run on a quantum computer again. And so there are two methods in general. The first one I explained, which is called gate cutting. We replace a gate by a sum over single qubit operations. And in this case, for example, we have this 4-qubit circuit, and it would decompose, disintegrate into a sum over independent 2-qubit circuits. And then additionally, there is a second method, which is called wire cutting, and where you basically replace a channel corresponding to a wire, so an identity channel, as a sum over measure and prepare channels. And by that, you can again cut this quantum circuit. Of course, this cutting doesn't come for free. You have to pay a price. Otherwise, quantum computing wouldn't make much sense. And the price you pay is in terms of sampling overhead, meaning that you need more samples or more shots in the experiment to estimate, for example, an observable to the same additive error. And you can calculate this sampling overhead in which we call kappa, by a sum over the absolute values of these expansion coefficients. And then the sampling overhead is kappa squared. And if you have k cuts in the circuit, then it's kappa to the 2k. So it grows exponentially in the number of cuts you do in the circuit. And then there has recently been a lot of work which try to find better decompositions in the way that they use, or they have less sampling overhead, or they use less ancilla qubits. And most of this work has been,
Is it always possible to do this kind of gate cut for any gate, for any unitary?
Yes, I think so. Okay. But you mean like so for two qubit unitaries, it's definitely always possible. You can actually write down explicitly an upper bound on the sampling overhead for the decomposition, but I don't know if it's generally possible for any qubit, any unitary. It is possible for, yes, it is possible. It is generally possible, but the sampling overhead might basically explode.
So it's that these single qubit unitaries actually, they span the space of all channels, or all unitary channels, something like that. Is that the
right? In principle, you could decompose any unitary of any size by using CNOT gates and single qubit operations, and then you could just cut all the CNOT gates. But this would be impractical due to a large sampling overhead. Okay. But yeah, as we will see, for some certain unitaries, such as multi-controlled set rotations, the sampling overhead is bounded, even if the order of the gate is very large.
I guess the catch is you need negative coefficients to do this.
Exactly.
Like
so
to decompose a CNOT gate, right?
It's a quasi probability decomposition of the gate. Yeah.
Okay. Thanks.
And yeah, also we cannot decompose a CNOT gate in a sum over unitary operations, but we also have to allow measurements and projections, as we will also see later. Yeah, as I said, most of the work was done for, or all the work was done for 2-qubit operations, and we tried to extend these ideas to multi-qubit operations such as multi-control set gates. And we did this by using ZX calculus. And I guess now I can show you how we did that. You can also find the results in that paper we put on the archive where you can find all the details. And as a very brief summary, in the end, what we have to do is we write ZX diagrams as sum over smaller or tensor products of ZX diagrams. So again, what we're going to do is, here's, for example, this quantum circuit with this 5-qubit control set gate. And we want to, for example, decompose it here in sum over 3-qubit operations and 2-qubit operations. And then this circuit here, for example, has this special structure where this 5-qubit control gate is the only connection between the partition consisting of the 3 first qubit and the 2 last qubits. So if we cut that gate, this circuit decomposes into 2 independent partitions. And just show you the main result, what we will find is that cutting this gate you can achieve by running a circuit where you replace it by 2 S gates, 2 S dagger gates, and so on. And there's also here this P operation, which then corresponds to some measurement operation. And next I'm going to show how we can do that. So what we use is ZX calculus and ZH calculus because we use this simple representation of multi-controlled set gates in terms of H boxes. So just to say the H boxes are defined here, and they correspond to 2 to the n times 2 to the m dimensional matrices, with all entries being 1. Only the lower most right index is a -1. And by that we can easily represent multi-control set gates. For example, here this, or can you see my mouse pointer, by the way?
Yes. Yep.
Okay, perfect. So this H box with only wires going to the right is a if we have n wires, it's a 2 to the n dimensional vector with only 1s as entries and 1 - 1 as the last entry. And if we contract it with these copy tensors here, then basically we copy that 2 to the n dimensional vector on the diagonal of an otherwise 0 matrix, and a matrix with zeros and only on the diagonal 1s, and as last entry a -1 is just the matrix representation of a multi-control set gate. And so the first step that we take is we write down the unitary channel corresponding to that multi-control set gate acting on an arbitrary density matrix rho. So we have here on the left the unitary acting on the density, and then the Hermitian conjugate acting from the right. I chose here a factorizing state. I don't know why I did this, because it's general, so it works for any density matrix here. And the first identity we use is the H-box fusion rule, which says that we can write an n plus m, or an H-box with n plus m wires, as 2 H-boxes with, or the tensor product of these 2 H-boxes, one with m and one with n wires, and they are contracted via this Hadamard gate. And this is basically a restatement of the Schmidt decomposition of such vectors with only ones as entries and one -1 as the last entry. And we just plugged that here into this expression. And so what you can see now is that if we call these first m qubits the partition A and the second n qubits the partition B, then these two partitions are only connected due to the fusion rule by this gray shaded tensor. And so we have reduced already the cutting of this m plus n dimensional qubit gate, or this n plus m qubit gate, into the cutting of this 4x4 tensor here in the middle. And now we could, for example, directly use that fusion rule to come up with this decomposition of a multi-control set gate, here shown for a CC set gate, for example. And we can write that CC set gate using two ancilla qubits as a CC set gate and a C set gate. And these two partitions are only connected by one C set gate. So we could reduce the cutting of an arbitrary size multi-control set gate to the cutting of one C set gate. However, in this decomposition, there's this factor of 2, and this makes the cutting inefficient, because if we have this left gate in a circuit and we evaluate, for example, an expectation value of an observable, then this 2 means that we have to evaluate the circuit where we have replaced the gate by the expression on the right side to an accuracy 4 times as good as the original one. And then with Hoeffding's inequality, 4 times better accuracy means we need 16 times more samples. And so using this decomposition is very inefficient, and we have to look for a different one. So next, the idea is the following. We replace this tensor, which I now call Q, by a rank 1 decomposition of factorizing vectors. So these factorizing vectors are these W and U single qubit vectors. And we plug that in. And now it's clear why we need factorizing vectors, because if they factorize, then we can flip that part. And now you see that we have effectively cut the gate, as these two partitions A and B are now not connected anymore. The only thing that we have to guarantee in using this decomposition of the tensor Q is that if we call that part here A, that if we contract this vector W with the Hadamard box and with these copy tensors, that then the resulting operation is either unitary, in this case it corresponds to a unitary gate, or a projector on one of the computational basis states. Then we can simulate it by measurements. If we find a decomposition in where these vectors W guarantee unitarity or projectors, then we are automatically guaranteed that the second part here corresponds to the Hermitian conjugate of the projector or the unitary. So this means that if this tensor A is a unitary or projector, then the decomposition is a decomposition into a sum over valid quantum operations that we can run on a quantum computer. And what we can do, one way to do that is we just expand this tensor Q in the Pauli basis and then write each of the Pauli matrices in its spectral decomposition, as shown here, for example, for the Pauli X matrix. And we also represent the identity matrix in eigenvalues of Pauli Y matrices. And if we do that, we define a decomposition set. So the first two states are the eigenstates of the poly X, the second of the Y, and the third of the poly Z matrix. And now we have to check if these elements in the set, when we contract them with the Hadamard box, if they lead to meaningful quantum gates or operations. And for all the X spiders, they do, because they lead to a multi-controlled rotation gate. The contraction with a spider, a set spider with phase pi, leads to a projector on the all-one state, but unfortunately, the only state that does not lead to a valid operation is this phaseless set spider. But we can now, if we allow an ancilla qubit, we can also simulate it on a quantum computer, as I can show you next. And credit goes here to John van der Wetering, who showed me, or who helped me with that and showed me how to do that. So what we do is we, instead of representing the Pauli X matrix in its eigenstates, we leave it as the Pauli X matrix, here shown as an X spider with phase pi. We shift it to the top, we introduce an identity and use the fusion rule. And this is, of course, a circuit. We also shift the connections to the Hadamard box to the right. And this is a circuit, and with one ancilla qubit, and we measure the Pauli X observable on the ancilla qubit. And if we do that, then and contract all the other spiders, then we find a decomposition of a general multi-qubit controlled set gate with a sampling overhead of kappa equals to 3. So that means that using this decomposition, we would have to use 9 times, so kappa squared times more shots to estimate the decomposition or the circuit containing the decomposition to the same accuracy as the uncut circuit. And this is the same sampling overhead you get for a CZ gate. And we know from previous work that for a CZ gate, this decomposition is optimal. So this is the lowest sampling overhead you could possibly achieve. But of course, we don't know if this is also optimal for higher order controlled set gates. And then in the final step, we can think about how to implement this decomposition without ancilla qubits. So we saw that the contraction of this phaseless set spider led to a non-valid or invalid operation. So we can just simply replace the Pauli X matrix by an by an identity matrix minus this set pi phase with set spiders with phase pi, and represent the identity by eigenstates of the set Pauli set. So in this, and by doing that, we have effectively eliminated the phaseless set spider from the decomposition set. However, this leads to a considerable increase of the sampling overhead. However, we don't have to use ancilla qubits anymore. And if we do that, then we find that general decomposition scheme I showed you in the beginning, which, again, I want to stress here that these circuit diagrams here do not correspond to the unitaries, but have to be read in terms of the channels, meaning that the channel corresponding to this 5-qubit controlled set gate is the sum over the channels corresponding to this S gate and this stagger gate and so on. And then I said before that we also need measurements, and this is shown here by this operation P, which is the sum over all projection operators on all the elements of the computational basis, and CL is always 1, only for L corresponding to the all 1 state, psi is -1. So this operation P is a non-positive, non-trace preserving map, but we can simulate it using post-selection.
Christian?
Yeah.
Could I ask you about the picture 2 slides back?
Sure. Here?
Yeah, that one. Is that thing on the right, is that something you're implementing?
Right. So yeah.
How do you implement that? Because I thought this was a picture of a state, and then you're doing something and it's adjoint on either side of it.
Yeah, sorry, this is wrong. This shouldn't be row, but it should be the observable here. So this corresponds to, I take an initial state, apply. So, sorry, yeah, you're absolutely right. I take the initial state, I add 1 ancilla qubit, I initialize it in the plus state, then I act with a 4 qubit multi-control set gate on it, and then I define an observable given by the original observable, and in the first qubit I have the Pauli X matrix. And sorry for that. Yeah, of course this is absolute rubbish what is shown here.
So you've sort of turned the thing inside out then, and now you've got the pure state on the outside.
Right. I wanted to write down here the right. Yeah. I wanted to write down here the expectation value when you act on the observable. But I guess then it's clear if with this information.
Yeah, I think so. I mean, but you still get a probability out, right? Not a.
No, I get, depending on what observable I choose, I get the expectation value of this observable with respect to that. If I define the observable as the original observable and the tensor product of a Pauli X matrix. And I mean, this single the outcome of this single circuit doesn't mean anything physically. It's only if I add up all the results of the single circuits in the decomposition, I get the meaningful result of the initial circuit that I decomposed.
So I can see how if I now put in my initial state and then I put the observable in the middle and then I post select on my final state, that thing is a number which corresponds to the expectation value. But what I don't see is how I could get that number, because I'll get, when I run this thing on a quantum computer, I'll get that amplitude but absolute value squared. Right, I'll get a probability out.
No, I'm not sure if I understand what you mean, because I don't look at the picture on the right. I just take in a state which contains 1 ancilla qubit, and I estimate or I sample the observable, which corresponds to the original and one Pauli X.
Okay, yeah, I get it now. Yeah, I think I'm still getting confused by the wrong picture.
Yeah, I will change it for the next talk. I'm sorry for that.
So you just prepare the state with an ancilla and then estimate now X tensor the original observable that you want.
Exactly. Yeah, this is what I have to do.
Yes. Okay. Yeah, that's clear now.
Okay. Thank you. Thank you for showing me that mistake. Yeah, right. And I guess where were we? Yeah, here, right. On the sampling overhead in general, using this decomposition, it's easy to calculate by just summing up these prefactors that in general, we can decompose any multi-control set gate with a sampling overhead corresponding to kappa equals to 6. So kappa squared would be 36. So we would need 36 times more samples in general, but it reduces if we go to lower order of the control set gate. For example, for a CC set gate, it would be 4.5. And yeah, then we also did some experiments, which I can show you next. So we first sampled a random circuit, and we added one CC set gate in the middle. And yeah, otherwise this lowest qubit is independent of the upper two qubits. And then we added some variable phi to the angles of a few of the single qubit rotations. And then we scanned through it and evaluated the Pauli set string on the 3 qubits. Then you see that the numerical exact result is this solid line. Then there is the triangles, which corresponds to the full circuit without circuit cutting. And then there's the green dots, which correspond to the results evaluated with the cut circuits. And you see that the cut circuits already seem to lie a little bit closer to the numerical exact solution. But this effect becomes much more pronounced when you go to, for example, a 5-qubit control gate, because in this case, the full circuit produces just random 0 results without information, while the results from the cut circuits still, at least qualitatively, match the numerical exact result. And the reason for that is that if you compile a 5-qubit multi-control set gate to superconducting hardware with CNOT gates as native gates, then you need many CNOT gates. And this directly translates into the impact of error. Because think about when we cut the 5-qubit control gate after the 3rd qubit, then all we have to do at most is to replace it by a two times controlled S gate and S dagger gate, and that has much lower CNOT gate count when we compile it. And this is the reason why we get here, using the circuit cutting, why we get some resilience to noise. And so this is maybe interesting to use that when compiling quantum circuits. So for example, you could simulate by circuit cutting a multi-control set gate which connects 2 qubits which are very far apart on the hardware graph, and then you could just simulate it virtually, so to say, by using circuit cutting. And yeah, maybe some ideas about further work we also look into. So it's interesting to see that some of or many of these multi-control operation gates or multi-qubit gates, such as, for example, general multi-qubit rotation gates, you can again use ZX calculus to write it in a form that only the 2 partitions you want to cut are only connected by one wire, so to say, shown here with this purple, shown here in this purple box. And so this would define this tensor Q you have to cut, like in the case of the multi-control set gates. You can also do that for multi-qubit rotation gates, and then you directly, again, using ZX calculus, you can also come up with decompositions for that. And then maybe one recent result, if you look into circuits that appear, for example, in the QA-OA algorithm, then there are these cascades of two-qubit rotation gates. And now you can do, so to say, parallel gate cutting by not cutting them individually, but cutting them simultaneously together, jointly. And this leads to a submultiplicative behavior of the sampling overhead. And it seems that also with using ZX calculus, it is much easier to see that than in using other approaches. And I guess with that, I'm at the end of my talk. And yeah, I think we have the time for discussion.
Thank you very much. If everyone could give a quick round of applause to Christian. And I will open up the floor to any questions. So please just take it away. You don't need to raise a hand or anything. Just fire away.
Yeah, I was wondering, these experimental results you showed, where you have less accuracy with the sort of a non-cutting method.
Yeah.
Is that taking into account the fact that you need more samples when you use your method?
Yeah. So these experiments were done where we keep the accuracy fixed. So in case of cutting, we need 36 times more samples.
All right. Okay. So. Right. So so if you were to take 36 more samples, would you expect that the original full circuit thing would get closer to your results? Or is this because it's like decoherent noise that wouldn't help?
This is noise. This is, yeah. So I expect that the results from the cut circuit would still be better, but I guess the variance would be larger. So these green dots would maybe shift randomly a little bit more. But we can, so to say, that the noise impact we can reduce. Only what we cannot reduce is the shot noise effect.
Okay. And before running, did you do like optimization passes on Qiskit stuff to see like there's a bunch of gates that could be combined to single rotation?
Yeah,
and stuff like that?
We did, but I think that it could have been better. It could have been done better. We didn't use I guess the most or the best methods to reduce CNOT counts for compiling these large gates. But it's also hard because so this picture here corresponds to a hardware with full connectivity. But when we ran it on the IBM device, we also have to these hardware constraints, only nearest neighbor interaction. So I guess I'm not sure if there are general decomposition techniques, optimal decomposition techniques of multi-control set gates on restricted hardware. I don't think so.
Maybe on like a linear nearest neighbor that there are results, but for like a general one, I don't think that's optimal. And so you when you do your cutting, do you optimize each of the individual circuits you get separately before sending them to the computer?
Yeah.
Okay. Yeah.
Do you know if there's any relationship between these circuit cutting techniques and things like stabilizer extent and stabilizer decomposition, those sorts of things?
So I'm not an expert on stabilizer formalism. Cannot say that.
So there's there's a work for this is in classical simulation of decomposing. Well, first you take, for instance, a Clifford plus T circuit and write it as a Clifford circuit with a magic state going into it, which you use to generate your T gates. And then you look at decomposing that as a sum of stabilizer states.
But is it also done in the sense of decomposing superoperators, or would you, in this case, decompose like only the state rather than the density matrix?
I think both is done. You can do either, depending on whether you're interested in simulating for mixed states. But the thing that made me think about stabilizer extent is the hardness there is based on the L1 norm of the coefficient. So the exact same kind of thing as you have, and it's really the negativity which makes it difficult.
Yeah, it's also the same in like probabilistic error correction, where you would also replace error prone operations by the error-free, or you would simulate them in this way. Then you exactly also get this quasi-probability decomposition. And yeah, I think so. This L1 norm makes numerics and optimization and also theoretical results very hard to achieve. If it was the L2 norm, then everything would be easy.
Have you looked into decomposing multiple multi-controlled gates at once? So like suppose you have several CCZ gates or multi-controlled CCZ gates where they overlap on some qubits and maybe they're next to each other, that like you can sort of like split them at the same time to only work with a subset of qubits.
I only have started looking into that. It works for CZ gates, but I haven't yet tried to generalize it to multi-control Z gates. So you get this sub-multiplicative behavior if you have, for example, a cascade of CZ gates and they share qubits. And so I suppose that it also works for multi-controlled Z gates.
Right, and then another question. So you have this other method that, for instance, that they cut a wire, right? Like it's sort of like they make an identity by doing a measurement. So if you were to do this on, say, this 5-qubit CCZ, then like in one case where you would get a get zero, the CCZ would disappear. So in that case, you can sort of not implement the CCZ and get a really cheap circuit. While in the other case, you would perform a 4-qubit CCZ, and then maybe you can do another measurement, split it again. So this would be sort of like a more interactive approach where you do intermediate measurements.
So can you say it again?
Maybe I'm like I'm not understanding enough how these other methods work. But suppose you execute the circuit, you get to the 5-qubit CCZ gate, and before that you can decide, okay, I will split this qubit by doing a measurement here, and then you need the measurement outcome to decide on what you want to do next, right? Or is that not?
So I'm not sure exactly what you refer to in this case of this other method, this wire cutting. You would
So I guess my underlying question is here you compare against not cutting the circuit. Have you compared it against cutting it in different ways?
No, we haven't. But at least from the perspective of sampling overhead, even for this 5-qubit gate, you would already have much more sampling overhead if you use that wire cutting. But we haven't compared it to other methods, like to the noise impact. Maybe the noise impact probably would even be less if I just cut all the wires. But this would mean that I have an extremely large sampling overhead, an impractical sampling overhead. So it also scales 3 or 2 to the k, where k is the number of cuts. So for 5, you would already have 2 to the 10 as sampling overhead. I don't know if this answers your question or if it was a different
I think
question.
so. Yeah. Thanks.
Okay, are there any further questions? I'm going to take that silence as a no, in which case, thank you very much, Christian. I'll give you a wee round of applause again. Let me just check. Yeah, the next couple of weeks are bank holidays, so we resume again on the 15th of May. So yeah, thanks, Christian. See you all in a few weeks. Bye.
Thanks.
Bye. Thank
Bye.
you.